Next, we will discuss how to do calculus with the arctangent function. Let's consider the arctangent function and let's find its derivative. Of course, we can use the limit definition of the derivative, however, we get stuck quick. So let's try the implicit differentiation instead. First, we apply the tangent function to both sides and then differentiate each side. On the left side, we use the chain rule, and on the right side, it is just the derivative of x. We divide both sides by the squared secant of y and replace y with the arctangent of x. We definitely learn how to simplify such expressions in trigonometry. So let's simplify this expression using the procedure that we developed in trigonometry. First, introduce theta by labeling everything inside the parentheses as theta. The original expression is not very simple in terms of theta. But what do we know about theta? From its definition, we know the domain of theta and can produce the following statement. Next, we recall the definitions of both involved trigonometric functions. Now, we can draw a reference triangle with theta in standard position and label the sides appropriately. We then use the Pythagorean theorem to find the missing side. And finally, we plug in the needed sides into the expression in question. After simplifying the trigonometric expression, we now have the following result. In summary, we now have the formula for the derivative of the arctangent function, as well as the formula for the antiderivative of its derivative. Now we can find the derivative of the following function. We start the process by recognizing that we have to find the derivative of a composition of the arctangent function applied to the natural exponential function, which is equal to the following expression, in which we know how to find all the components. We get the final answer after simplifying. Let's do another example. We again start the process by recognizing that we have to find the derivative of a composition of the natural logarithm applied to arctangent function, which is equal to the following expression, in which we know how to find all the components. And we don't need to simplify anything here. Let's do an example of integration. We first recognize the pattern and rearrange the integrand. Then we set up the substitution by setting a new variable, let's say t, equal to the arctangent of x, and finding the differential of t. Next, we plug everything into the original integral, and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function arctangent back for t. Let's do an example of a linear substitution. We set up the linear substitution by setting t equal to 3x and finding the differential of t and expressing dx in terms of dt. As a result, we have a simple indefinite integral in terms of t. We continue with the integration process by finding the antiderivative and replacing t with the original function. We discussed how to differentiate and integrate the functions that have the arctangent as one of their components.